Okay, in this video we're going to look at what is known, the required practical is about the ripple tank, which is in a separate video, but we're also going to, in this video, just look at some of the key ideas to do with the wave equation, and then we're going to look at what happens with reflection and refraction, and we're going to describe them using what's known as wavefront diagrams. But first, just a little bit of quick revision about the wave equation, and we know that for a wave, to calculate the speed of the wave, you have to multiply the frequency measured in hertz by the wavelength measured in either meters or any other unit of length that we're going to do today. We're going to actually look at it in terms of millimeters. So what's this results table here we're going to try and fill in, and we're going to use a simulation. It is quite time consuming, so I'm probably just going to do A, and then I'll very quickly go through B and C so you can see the results. But if I just change onto this is the animation that we're going to use, and we're going to look at this particular wave, which is wave pattern A. So this A here means the wave pattern A, and we're going to look at things like the time taken for 10 waves, the period of the wave, frequency, wavelength, etc. So if we go along, and I'll do these one at a time. So the first thing we're going to do is work out the time taken for 10 waves. So we've got a stopwatch here, and if I sort of hold my mouse here, we can look at when a wave passes. So that'll be 1, and then 2, 3. Okay, so what we're going to do is I'm going to start the stopwatch, and I'll count to see how long it takes for 10 complete waves. Now when I start the stopwatch, I've got to remember to count the first wave, so I must be careful not to count and start at 1. I need to start at 0 and then 1. So if I just do that over here, and if you watch as a wave goes by, I will count as I'm doing it. So I'll go start, and that's 1, then 2, then 3, then 4, then 5 waves, 6, then 7, then 8, then 9, and I'm going to get ready to stop. So it's about 16.3 seconds. So I've got slightly different times. Last time I did it was 16.4 seconds. From this I can work out the period of the wave, and if this was the time for 10, all I've got to do is divide this by 10 to give me 1.64, and that's the period, which is the time for one wave. I could then work out the frequency, and the frequency will be how many in 1 second. So if it's 1.64 seconds for 1, if I just go 1 divided by 1.64, and I get an answer of 0.61. So that's how many there are in a second. So that's the frequency. Now I need to measure the wavelength, and we'll stick in millimeters. So if I just pause this, okay, if I try and pause it around there, then what I can approximately do is, using the ruler across the bottom, I can measure the wavelength, and you can see there I'm just across the top, so I'm going to be sort of just about here. So if I come down, that's about 50. Alright, I can move that in a little bit more, and I can say, right, if I started from there, you can see it is just about 50 millimeters. So the wavelength here will be 50. Now I've got to do some timing again. I've got a time for how long it takes for the wave to travel 200 millimeters. So you can see the length of this ruler between X and Y is 200 millimeters. So if I reset my clock again, get the wave moving, then this is a bit harder for me to show you, but I'm just going to watch one peak as it goes across the screen, and start and stop as the peak starts at X and ends up at Y. So I'll just do that. Okay, I'm going to start it now, so I'm just watching that peak going across the screen, and it's nearly there, and I'm going to stop it now, and I've got about 6.6 seconds. So last time I did this I got 6.4, but it's not too far away. Obviously it depends on exactly when I've clicked it. So now using this I can do the wave speed from distance divided by time. Then I can say it's 200 millimeters in 6.4 seconds. So 200 divided by 6.4 is about 31. Or I can use our wave speed from our equation, that speed is frequency times wavelength. And if I go frequency is 0.61 times the wavelength is 50, and if you do that I also get an answer of about 31. So you can see, using the wave equation, I've shown that the wave speed is the same as if I do a more classical distance divided by time. And on this animation there are 3 different waves, so that's wave B, and some of the results down here. And again, if you want to pause the video, you can just sort of stop and do the calculations. And then wave C is a slightly different wave. Get it going again, and again here are the calculations, or the data and calculations for C. So just a chance to start off and revise some work on the wave equation. But the main reason for today's lesson is looking at wavefronts. I'm going to look at wavefronts in both reflection and refraction. And the idea is that if you look on the base of a swimming pool, you must have seen this before, where you get these white or lighter areas and then darker areas. So as the light comes through the water, something's happening where more light is sort of being focused into some places than others, and this is because the light is either reflecting off the surface or it's refracting through the water, and some of the light is it's changing direction dependent on the peaks of the wave at the top. So that's kind of the linking this to the real world. But let's just do the easy one first. We'll do reflection. So far we've looked at waves as rays of light travelling in straight lines. We can also think of them as being like a ripple on a pond, or what's known as a wave front, and it might help with this animation to think of it as a line of little balls being thrown at the wall. So imagine this along this line, if you had literally 10 or 15 balls all moving straight towards this wall, and hopefully if I just let it run, the balls will get closer to the wall, and then the ones that hit it first would bounce off, and then the others would bounce off. So you get these balls in a line bouncing off, and if you think about it, they would all come off at the same angle that they went in. Now, a slightly easier animation if I show you here. So there you go, that's the idea, look. Okay, that's our incoming ray and our outgoing ray, our reflected ray. And what we can do here, if I just show you this one, I will reset this so it's nice and straightforward. And if we get some waves coming in, and imagine these are a line of balls coming through, and then as they hit, you can see they bounce off. Okay, so they're coming in and they're bouncing off. And what I can do on this is quite nice. I can change the angle of the wall. So if I change it to about 45 degrees there, if I can just get it on, you'll see that this is a classic reflection where they're coming in and going out, so it's going round 90 degrees. With the mirror at 45 degrees, it's going round 90 degrees. And if I put some this on, this might remind you of the work we've done on reflection in the lab. So if we treat this as a single ray of light, and as this is a mirror, you'd have, here's the normal line at 90 degrees, and you'd have the angle of incidence is equal to the angle of reflection, which is in our case is 45 degrees. So we can describe this as we have done with a single ray of light, but the idea for today is to describe this as what's known as a wave front. Okay, so that's this one. If I now move on to refraction, this is a bit more harder. We've talked about refraction in previous videos, that refraction happens because the wave changes speed as it enters a new medium. So here it's going to go through this air and go through this glass block. So can you predict what will happen to the wave as it enters the block and it slows down? So let's have a look and we'll see. So as it enters the block, it starts to slow down. So the point where it enters the block, the wave slows down, and what that does, that causes the wavelength to get less. So the wavelength decreases, and then as it leaves the block, it speeds up again, so the wavelength increases. Now what we can show on this, so this is how you draw your light. So it would bend towards the normal, and then it would bend away from the normal. So on the more complicated animation, if I just do this with the block, you can see as the wave fronts, remember we're talking about wave fronts today, as the wave fronts hit the block, they're slowing down and the wavelength decreases, and as they leave the block they speed up, so the wavelength increases. And interestingly, the frequency stays the same, because if I just put my mouse here and count, when one goes past, you'll see it's 1, 2, 3, 4, 5. If I do that in the block, I'll put my mouse somewhere here in the middle. It's 1, 2, 3, 4, 5. So the frequencies staying the same inside and out the block, but it's the wavelength and the speed that's changing. Okay, and if I put in that, and I think somehow I can change the angle, so you can see as you'd normally draw on the previous screen, this is how you'd normally show refraction, and it speeds up as it comes out. And if I do this, you can see this is where, linking it back to our refraction lesson, the angle of incidence here, and this is the angle of refraction, and it bends towards the normal on the way in and away from the normal on the way out. So in terms of what you've got to do, We think it's going to be something like this. So which diagrams are correct? You've got A, B and C for reflection, and if you think here, these are the wavefronts coming in and they appear to be going out at a different angle, so that doesn't seem to be correct. With B, we've got the wavefronts coming in and they are being reflected at the same angle, so that looks as though it's correct, so B is definitely correct. C, they're coming in and they're going out at a different angle, so that's incorrect. With the refraction, this is going in at an angle, so what these wavefronts should bend towards the normal, or they should slow down so the wavelength decreases, so 1's definitely wrong. If we look at number 2, this here, it seems to be going the wrong way, doesn't it? Because as the wave comes in, it seems to be bending away from the normal rather than towards the normal, so 2's not right. Let's have a look at 3. It comes in, it bends towards the normal, and then it goes away from the normal as it leaves, and you can see the wavelength has decreased as it goes in. So this is the correct one, number 3. Okay, so this is just taking your knowledge of reflection and refraction and applying it not just to rays of light, but thinking about it in terms of wavefronts that you've seen in the ripple tank required practical, and also on these diagrams that you will be expected to recognise.